Today we're talking about the kinematic equations that we get when acceleration is constant. We'll also look at a case of constant acceleration called freefall. And we won't go over examples here, but in the next video we'll have examples for kinematics in general, plus cases of constant acceleration, and using all of these equations that we go over today. I won't be deriving the kinematic equations since the derivations can be found in a textbook and online. They can be obtained using algebra and substitutions, but also with calculus, so you can find the appropriate derivation if you'd like to see it. The first equation I'll write is not only for constant acceleration, but when the acceleration is always zero. Here, the final position I've written as s, but we could replace it with x or y depending on the direction of our motion. It is given by the initial position s0 plus velocity times time. Now this equation is really just saying what we mentioned in the last video. The final position is just equal to the initial position plus some change in the position. In this case, that change in position is equal to the velocity times time. This makes sense. The change in position is just how fast the object was traveling and for how long. And notice this is just a rearrangement of our equation for average velocity. We could also drop the zero in the subscript here since the velocity won't be changing if there is no acceleration. This is the only equation we need if we're moving in a straight line with no acceleration. But what if there is acceleration? Well, our final position is still the initial position plus some change in the position, but now that change will depend on how fast we were going initially and how much we accelerated. So now we need this velocity to represent the initial velocity with our zero as a subscript, and we'll add on a term that accounts for the acceleration. Now our second equation is similar. It says the final velocity is equal to the initial velocity plus however much our velocity changed. And the change in velocity depends on how much the object was accelerating and for how long. The third equation looks a little bit different. This equation we get by substituting in order to remove time from our equations. There are cases where we may not know the time interval traveled, and we want a relationship between the velocity, acceleration, and the change in position. So if you don't know anything about time, this equation comes in very handy. In some classes, these are the only three kinematic equations that are covered. And these are enough in many cases, but we can get a couple more that will allow us to solve a few more problems. The next equation is very similar to the first equation. In this case, the velocity is the final velocity instead of the initial velocity, v0, and we're subtracting the term accounting for acceleration rather than adding. This equation is found the same way as the first, but it's like we're working backward. So imagine if we knew where an object ended up, how fast it was going when it arrived, and how much it was accelerating. We should be able to figure out where the object started in the same way as we would solve for where it ended, just working backwards. The final equation just involves rewriting our equation for average velocity. Average velocity is the change in position over time. But as long as acceleration is constant, we can also write the average velocity just using a mathematical average, where you sum all of our values and divide by the number of values we have, the same way you would find your average grade, for example. In this case, we can take the initial and final velocity, which are two velocity values, and add them together, and then divide by 2. Plugging in and rearranging, we get this final equation, which, notice, it accounts for the acceleration using average velocity, but it does not explicitly have acceleration in the equation. And now let's look at all of the equations together. Notice each equation is missing one of the quantities we use to describe motion. In solving problems, we often don't know everything except for what we're solving for. If we do, there may be multiple ways of finding what we're looking for. Otherwise, we'll want to find the equation that has what we're looking for, plus it involves only quantities that we know the values for. The best way to get familiar with these equations is to use them in some example problems, which we'll do plenty of later. But for now, let's look at some specific cases where we'll use these equations and talk about them in general. When an object's motion is only being influenced by gravity, it is said to be in free fall motion. Gravity always pulls objects toward the surface of the Earth, so it accelerates them downward in the negative y direction. It turns out, as long as an object is near the surface of the Earth, which is where we experience most of our lives, this acceleration is approximately constant. We call this acceleration gravitational acceleration, and it is equal to 9.8 meters per second squared. Notice gravitational acceleration is a positive number. You can think of this as the magnitude of the acceleration. Now we write the y component of acceleration, a, as minus g. And here the minus sign gives the downward direction. This is a common mix-up, so be sure not to get confused where the minus sign goes. Since we are only looking at one-dimensional motion for now, objects in freefall fall into three categories. They are either dropped from rest, which is like when you hold up a ball and open your hand and just let it fall, or the object is launched straight upward or launched downward, which is like when you're throwing it up or down. We'll discuss objects that are launched at an angle and move through 2 dimensions once we are comfortable with one-dimensional kinematics. In either case, it's important to remember the object is not being influenced or touched by anything but gravity, including air resistance. This is an ideal case, and it's an approximation. If the object is coming into contact with anything, it's no longer in freefall. So if you throw an object straight up, and then you catch it when it comes back down, we only consider the motion right after it leaves your hand and loses contact until the time just before it strikes your hand on the way down. This means the force you applied to accelerate the object to some speed initially is ignored. The object will also stop once it hits your hand or the ground or something else. All of this is ignored too. So our initial velocity in this example is the speed it leaves your hand going upward, and the final velocity is the speed just before striking your hand going downward. It's easy to think, oh, the object stops once it hits your hand, so the final velocity is 0. But the moment the object touched your hand, it was no longer in freefall. Now let's take our general constant acceleration equations, or kinematic equations, and plug in our acceleration since it will be constant and the same for all objects in freefall. Since freefall motion is only in the y direction, we will replace our coordinate s with y in each equation. Then we will replace the acceleration with minus g. Now the equations on the right will all apply to any object in freefall. Notice we have already put in our minus sign. This means when we go to plug in values to solve our equation, we just need to put in a positive 9.8 in for g. We have already accounted for the minus sign. It's also nice because we always know the value of acceleration, so it's never something we're looking for. The only things we could possibly be solving for is final or initial velocity, final or initial position, or the time interval of motion. Now let's look at something we might want to find in a freefall problem, the max height reached by an object. We'll take the case of an object thrown or launched upward. First, notice in 3 of our kinematic equations, I've written y minus y naught, so the final and initial positions are separate. These can also be replaced with delta y when appropriate. For example, we may not care about the specific height the object started or the specific height it reached. We may only care about how far it traveled upward. In that case, we could just use delta y instead of having y and y naught separate. Or you may only be given how far up or down the object traveled in the problem statement, but are never actually given coordinates or specific positions. This is okay, and it's also very common, so just know that sometimes you may find it useful to rewrite y minus y naught as delta y. So if you're finding the max height for an object launched from the ground, you could call the initial height 0 since it is on the ground. Then the max height, y, and the distance, delta y, are essentially the same thing. Now, I'll highlight y in yellow to represent that it's what we're looking for. We'll assume y naught is either given or it can be combined with y and written as delta y, so I'll highlight it in blue, as if we already know it. We always know the value of g, so I'll also highlight it in blue along with the other constants. We can look to see if we have enough information to solve for the max height right away. We can't use our second equation since there is no position. So out of the initial and final velocity and the time, we'll need at least 2 of the 3 to solve for the max height. If you don't have these, then we'll need to start finding them until we have enough information to solve for max height. This is often when students get stuck because there are multiple equations to try, multiple other quantities you could solve for, so where do you start? Well, we haven't written down everything that we know just yet. And this not only makes problems overwhelming sometimes, but sometimes it can make them impossible to solve. If our problem starts with us launching an object upward, and it ends when the object reaches its max height, then what is the final velocity when it reaches the top? Well, it has to be 0, because otherwise the object would either still be moving upward, or it would already be on the way down. This means we have more information, so I'll highlight the final velocity, Vy, in blue since we know its value. Now there are only 2 other pieces of information you could be missing, and you likely started the problem knowing at least one or both of these. There are other things that you know that may make this problem easier. Maybe you've been given information about the object's entire trip as it went up and then returned back down. For example, say you're given the total time of flight the object is in the air, meaning on the way up and the way down. Well, because the acceleration is constant, the object will accelerate the same amount on the way up as it does the way down. This means the time it takes to go up is the same as the time it takes to go down, as long as it's returning to the same height. And that means the time to reach the max height is just half of the total time of flight. And now we have a new piece of information to solve the problem. By this same logic, we can see the speed at which the object is launched upward is the same speed as when it returns to its original height, because it speeds up on the way down the same amount as it slows on the way up. This is true at every height. However fast it was going at that height on the way up, it will have the same speed when it returns to that height on the way down. Understanding freefall motion is all about using things you know, even when they are not explicitly given. The problems you work also won't remind you of these things, so it's important to remember them. This is part of knowing the physics of solving the problem. Let's go over things that you should remember and things that you shouldn't get confused about. First, we must remember the acceleration is always known in freefall problems, and it's equal to minus g. We just need to be able to recognize when an object is in freefall. If you're given the equations with minus g already plugged in, just remember that g is a positive 9.8 meters per second squared when you're plugging in. Otherwise, you won't be given any information on the acceleration because you're expected to know the acceleration for an object in freefall. Second, this acceleration is the same everywhere, which is what we mean by constant acceleration. This means the acceleration is always downward, and it always has a magnitude of 9.8 meters per second squared when the object is moving upward, when the object is not moving at the top, and when the object is moving downward. So don't confuse the direction of motion or velocity with the direction of acceleration. They are different. Next, the speed at max height is always zero, because this is what it means to be at max height. Again, if the speed was not zero, the object would still be moving up, or it would have already turned around and started moving down. When an object goes up and falls back down, the time up equals the time down for the same height. The speed on the way up equals the speed on the way down for the same height. Notice that I didn't say the velocities are equal, because on the way up, velocity points up, and on the way down, velocity points down. So remember that velocity is a vector, and you have to flip the sign. A few other things. When you see the phrasing dropped or released from rest, this means that an object started with no speed, and then gravity accelerates it to start it moving. Mathematically, this means v0 is zero. So this is the way the problem statement might give you information without explicitly giving you numbers. Next, the time of flight is the total time spent in the air, both up and down. Time of flight and time to max height are not the same. When the object returns to the same height at which it was released, then the time to max height is equal to half the total time of flight. And finally, don't confuse velocity and acceleration or position and velocity. Velocity and acceleration can be in different directions. The direction of acceleration only depends on the change in velocity, not the initial velocity value or final velocity value. The signs of position and velocity can also be different. Just because you're at a negative coordinate does not mean you must be moving in the negative direction. Let's quickly look at directions of velocity and acceleration, since these are easy to confuse. When velocity and acceleration are in the same direction, the object is accelerating in the same direction that it is already moving, so it speeds up. We represent this with a longer arrow. And if the acceleration is constant, the length or speed will continue to increase in the same direction. When the acceleration and velocity are in opposite directions, the object is accelerating the other way. We often call this deceleration, but technically it's just accelerating in the opposite direction that you're moving. This causes the speed to decrease. If the acceleration stays constant, eventually the object will slow down and come to a stop. And again, if the acceleration continues, the object will start moving again, but now in the direction of acceleration. Then we are back to the same case where the velocity and acceleration are in the same direction. So the object will speed up in this new direction. This is the same thing that happens when an object is thrown upward in free fall. The entire time it is accelerating downward. So while it's moving up, it slows down. This continues until it stops, which is when it reaches its max height. Then it begins moving in the direction of acceleration, which is downward. And it continues to speed up until it encounters something to stop it. So acceleration does not tell you the direction an object is moving. It tells you the direction the motion or velocity will tend to. In every case we have drawn, the velocity always changed to become more and more in the direction of acceleration. It's often helpful to think of slowing down to the left as speeding up to the right. This way of thinking may feel odd at first, but it's a very useful thing throughout physics. In the next video, we'll go over examples for one-dimensional kinematics in general, as well as constant acceleration and free fall. So that's it for this video, and I'll see you in the next one.